Good evening, everyone. Welcome to CoffeeJUG Online. Today, I'm excited to introduce you our speaker, Andrii Rodionov, who will be sharing his insight about distributed systems. As always, a warm welcome to everyone. And first thing first, we want to remind you that don't forget to support Ukrainian armed forces. Remember that even a small contribution could make a huge impact. Uh, Over the years, we have grown together, hosted more than 50 unique events with more than 700 participants, and your personal involvement made all of this possible for us. Thank you. Special thanks to our organizers team, Igor, Uliana, Olesa, and Oleg, and to our community partner, JetBrains. Uh, and wish you a good talk. See you later. And Andrii, stage is yours.
Okay, hello, good evening, everybody. So, at the last moment, we decided to switch from Ukrainian language to English language. Yes, and sorry for Ukrainian audience. Perhaps the talk will be not so excited as it will be at my native language, but I hope for another visitors from abroad, yeah, will have more takeaways after it. And a little about me. Currently, I am joined a new company. It is modern company. It is not the vaccine from COVID. It is tool that helps company to update their code base and move from old codebase version to the new codebase version. Yeah, I joined it one week ago, so I haven't put it yet on my slide deck. But besides this, I am the lecturer at Ukrainian National Technical University, and those are who is from Lviv. It is from also I'm from Ukraine, reading the set of lectures at Ukrainian Catholic University. And in the past, I was a software engineer in Hazelcast. And most of my talk will be dedicated to 3 years of my experience that I had at Hazelcast. And I will talk about my own experience. Yeah, and the problems that we have personally faced. So it will be not talk about promoting Hazelcast, yeah, but it will be what can happen in a real production ready and quite popular distributed system. Okay, let's go. And first of all, let's start from the so-called distributed system postulates. You definitely know about the postulates of relative mechanics, and some of them are also valuable for the distributed system. What are those postulates? The first is that the communication speed is limited of the speed of light. Yeah, it is obvious, but it tells us about the upper limit of the communication speed, but we have the limit from the another side of this line. So we couldn't definitely know what is the minimal communication speed, and in depending from the network and from the what kind of cloud providers you use, this speed may be very, very poor, especially if we design or we build our network, or our customers build their network from the scratch. Their communication speed can be very poor, not depending from the name of those customers or the network equipment. And we faced this problem with Hazelcast, and we discussed this later in our talk. The second postulate is that the time is relative. Yeah, what does it mean? It doesn't mean that there is no global single time and no global single clock, and it is very problematic to synchronize several clocks that running on different servers or computers. That's why in most so-called distributed algorithms, the time and timestamp not using in during making the decision. For now, there are several ways how we can get the true timestamp, and cloud providers like Google or AWS provides the quite good timestamps, but it is also with some boundaries. So in our algorithms, and the most algorithms were designed without taking apart the timestamp into account and trying to replace this timestamp some using other ways. And the last one, not directly related with with relative mechanics, but it is related also with two separate parts of some systems, and this so-called FLP theorem told us that it is impossible in a distributed environment knows what as a member or as a node or as a server currently doing. Is it available or is it not available? The only way to know this is trying to communicate with this server. But when you're trying to communicate with this server, remote server, the problem may be not with those server, the problem may be with the network. And those FLP theorem say us that it is impossible to distinguish network problem from the remote node problem. And for many customers, it is hard to understand how it is possible, how it is impossible to distinguish it. But if you, if assuming that you have no third party observer on our system, it is impossible from the point of view of this server recognize what is where is the problem. Is it in this network or is it the remote computer? Because the only way that you can communicate and ask the state about the remote computer is trying to use network. That's why it is impossible to distinguish this kind of failures. And with those postulates, let's move to our agenda for today. For today, we will talk about replication problems, how we can lost data during during replication, and replication guarantees. And then we move to the network problems like reordering, message duplication or deduplication, latency during communication, and the big part of our talk, of my talk, will be dedicated to Raft protocol pain points, because I have spent maybe around 2 years struggling with our implementation in of Raft protocol in Hazelcast. So before we start moving forward, let's try answer the question. It seems the obvious answer, but maybe the obvious answer is not correct in all situations. And the question is, in 3-member cluster, what is better, to have one slow follower or member, or to have two slow followers? The obvious answer is that, it's definitely that one slow follower should be better. But after my talk, maybe your opinion and my opinion will change, because for me, when before I am faced with this situation, my answer also was that it is obvious that one slow member in a cluster is much better than two. But we will discover the situation when two slow member is better than the one slow member. Okay, and before we start, I provide some background about the Hazelcast platform, because all of my examples with problems in distributed system will be based on the Hazelcast platform and the Hazelcast product. So some quick introduction about it. So Hazelcast has been started as a product as a distributed in-memory cache. Why it is distributed? Because there are 2 points why it is distributed. One of the point is that it is in memory platform. So to hold a lot of data, you should have several separate members or servers or not. Otherwise, the cache size will be limited the memory. And the second reason, it is for availability guarantees. If you have one member with something in memory and this member dies, so all memory also will be erased, and all data will be lost. And that's why Hazelcast, when you are creating the cluster, automatically create backups copy for data and use for this another cluster members. So Hazelcast has been designed as a distributed in-memory cache, and it has been used and continue to be used as this platform till now. After this, the first version of this distributed in-memory cache has been implemented as a distributed map that provides only availability guarantees. If you're familiar with CAP theorem, it is the AP part of the CAP theorem, and provide availability but not provide strong consistency guarantee. So your data in most cases will be always available, but there is no guarantees that the data is consistent on different members of this cluster. A little bit later, I will show you an example how it is possible that the system and the data can be inconsistent. After several years, there had been added additional implementation, and additional data structures have been added for the Hazelcast cluster. And those data structures are based on so-called strong consistency parts of the CAP theorem, and provide linearizable guarantees. It means that cluster guarantees that those data are the same on all members of the cluster members. And if you lose some member, the data will be the same on another member, and that property is called like strong consistency guarantees. And to implement this strong consistency guarantee, you should use some consensus protocol like Raft, Paxos, or ZAP protocol. In Hazelcast, we have our own version of Raft protocol, and those data structures are consistent data structure are based on implemented on top of this Raft protocol. And a year ago, in Hazelcast, there has been added also distributed map based on this Raft protocol that provide strong consistency guarantees. So for now, in Hazelcast, we have AP-based map that provide availability is fast but not consistent, and we have the strong consistent map that quite slow but consistent. Yeah. Okay. On top of these distributed maps, there have been built so-called real-time streaming process engine or streaming platform. This streaming platform provides a very nice API that you could apply some transformation, aggregation, combination, and so on operation on a stream of incoming data. From where this data could arrive, it is a bunch of sources. For example, the most popular is Kafka and CDC connectors. And after this, after transformation, the data could be synced into another part of to another systems or databases, or could be synced into the Kafka destination after transformation. And also there are a bunch of clients that you could use to connect and to Hazelcast and use and clients and use it inside your products and so on. So it was the high-level overview of the Hazelcast platform. And to implement this, we implemented it from scratch on Java without using some other frameworks or platforms. So it is implemented on a pure Java. Maybe one of the external used libraries is JSON converters. All other things has been implemented from scratch on using the pure Java. So we have in Hazelcast our own network primitives, our own serialization approach and schema catalog. We have our own RPC remote procedure call or remote procedure method invocation. By default, it is async, but if you are blocking, you put it into the sync model. Also, we have our own concurrency primitives. Unfortunately, they are based on top of completable future, so it is extension on top of completable future. Perhaps in future, the Hazelcast guy maybe re-implement them using the project Loom, because completable future is really painful, especially if you use completable future on top of some network connection. So you make the remote call and waiting for the answer using completable future, that inside of this completable future also wait for the network response. So that's why we had to extend these primitives to also take into account some network problems and network delays. Also, we have our distributed data structures and those data structures implemented, as I mentioned before, using two approaches. One of these approaches is best effort replication, like AP data structure, and another one, it is strong consistent based data structure that based on top of and implemented on top of Raft consensus protocol. They are called CP data structure. In our talk, we will talk a little bit about AP data structure, but most of the talk will be dedicated to CP data structure because the most problems that I have faced during my work at Hazelcast, it was related with those data structure because why is it? Because AP data structure are not so dependent from the network connection, and most of them are used async approaches in the internal implementation. With CP data structure that requires the strong consistency and the strong consensus, we are putting our system into synchronous mode with and should wait some responses from the another members from using network connection, and that's why the CP data structure and CP the operation on CP data structure they are mostly blocking in the internal implementation and very dependent from the network and network latency. That's why when we are trying to put our cluster in different availability zones, it becomes quite painful, especially for those CP data structure. But I show this later in our talk. Okay, let's start talking about the problems, and we start from the replication. I will show the couple of issues in our GitHub repository, and you can check and you can verify what was the exactly fix for those issues. And definitely I will explain what is the issue about. So let's start with this issue, and this issue said that something has been corrupted after something has been forcefully terminated. This issue is related with streaming part of the system, and I will explain what happened during this issue. So as I mentioned before, Hazelcast provide so-called real-time streaming processing capabilities, where you can put the stream of the data into Hazelcast. Hazelcast will apply some transformation of those data, of the stream of data, and then sync this data in some sync endpoint. As Hazelcast is provide the availability and reliability guarantees, it should guarantee that if during this stream processing data, if during this operation, for example, the one of members fail or going down, the data and the state of this stream will be not lost. So how this is implemented? It is implemented by replicating this stream state to other members. So if this member fail, in theory, another member should become the coordinator, and all data and all clients will be redirected to this member, and this member should continue from the same state that was on the failed member. It is in theory, and what happens in practice? In practice happens a situation that this replicated snapshot of the stream is not consistent with the old one, that was on coordinator. So some data during the replication has been lost, or not all snapshotted data from this coordinator reach this member. Why this is happened? This happened because in our implementation of the stream processing, the job and snapshot replication is based on IMAP. As I mentioned, IMAP is AP best effort data structure that in theory not guarantee the consistency. So it can provide only the best effort to replicate the data, but in particular cases, it is not guaranteed that data will be replicated in a consistent way. We even couldn't mention this AP data structure as eventual consistency, because the eventual consistency guarantees us that eventually all data from one member to another will be replicated. In our case, the data from coordinator can be completely lost during the replication. How this could happen? This is a small example that with timeline that can explain us the reason. So on this timeline, we have two clients that can write or read data, and also have three Hazelcast member. With these three members, it will be the Hazelcast 2 member is a backup for Hazelcast 1. And when the client put some data on the Hazelcast 1. Hazelcast 1 is so-called not leader, but master member. So all requests from clients redirected to this master member. And when the client puts some data, this data will be written first at the first phase to this Hazelcast 1, and this Hazelcast 1 will replicate this data on a Hazelcast 2 member. After this, the Hazelcast 1 wait for acknowledgement from Hazelcast 2 to respond to the client, and the client receives the response when actually data will be present on Hazelcast 1 and Hazelcast 2 member. This is the best scenario. If another client would like to read data, it also will be redirected to the Hazelcast 1 because it is the master member. So it is the best case scenario. But what will happen if, for example, something happened with network connection to the Hazelcast 2 member, or Hazelcast 2 is not available at this moment? Perhaps it is restarted or something else. Or, for example, message is lost somewhere in the network. In this case, the client also receives the acknowledgement from the Hazelcast 1, from Hazelcast master member, but this acknowledgement will contain some additional small message that there was an error while we are trying to replicate this data to Hazelcast member 2. But the client, if the client would like to analyze response from the Hazelcast, it could figure out that there can be the problem with the replication. But if client will not take attention, will not pay attention for this additional response parameter, it will not even consider that something can happen. But can happen. But otherwise, the client receives the response. And if another client also try to read this data from the cluster, he also will be redirected to the Hazelcast member 1 and successfully read the data. Everything is good until this Hazelcast 1 member is going down or crashed. If this happen, all another member from the cluster, and it will be Hazelcast 2, become a master. And all requests will be redirected to this master. And what we can see that client 1 receives the acknowledgement that data has been successfully put it into the cluster. Client 2, when he reads the data, the first request return him the data, but the second request from the client to return that there is no such data. From the point of view of clients, clients don't know about our internal cluster internals. From their point of view, the first request returns the data, but the second request that is started from the same client suddenly returns the empty response. And this is the problem with AP data structure and with so-called best effort replication. In our case, with this issue with stream processing data, there functionality for data replication and snapshot replication has been implemented on top of such unreliable map. And there has been happened something like I have described it on this picture. That's why the data and the snapshot state has been lost. What we can do, how we can prevent this? We shouldn't build our high-level solution based on non-reliable primitives. So if you are building some distributed system and you would like to have strong consistency guarantees, you should use some products or some platforms that provide you such consistency guarantees. Maybe the most popular is Apache Zookeeper. Apache Zookeeper internally also implemented consensus protocol. It is ZAP protocol. Or those systems should be built on top of Raft protocol. For example, in Kubernetes, they use etcd to store the metadata for Kubernetes cluster, and etcd internally used internally implemented the Raft protocol to guarantee consistency and data. Kubernetes data, metadata will be not lost. So when you build some high-level system, please take into account what primitives, especially distributed primitives, are you using. What another options you can have? It is majority write plus majority read. It is in MongoDB and also in Cassandra. You can configure that reading that write and reading mode for when you put and try to read data. That means that you are trying to read to the majority from 3 members is 2 members, so we are trying to read and to write and read from majority, that in definitely some member will be an intersection of read and write operation, and that's why we could guarantee the consistency of the data. But there are still some place of inconsistency with this approach. That's why Mongo and Cassandra have additional so-called linearizable guarantees mode that's built on top of some of consensus protocol, like Raft in MongoDB, and in Cassandra they used Paxos protocol. Talking about the consistency guarantees, there is no single white and black side of consistency, as there is no eventual consistency and strong consistency. Like in traditional databases, there is no there are additional level of consistency between serializable and read uncommitted modes. Yeah, there is some repeatable read committed and so on, depending from the particular database. And the same are in distributed databases or in distributed consistency guarantees. There is a top level and the most strong guarantee. It is linearizable. It is mentioned as a strong consistency. But with the strong consistency, you will have the poor performance, but you will have the guarantee that your data is consistent and the same and at all members. But it will be huge impact on performance of such system. If you would like to have performance, we should relax consistency guarantees, and we can relax it until we will have so-called eventual consistency, or we can have absent of consistency at all. So it depends from your situation, from your problem, from your requirement, from your data, what consistency guarantees you would like to have. For example, for financial information, the linearizable level, the strong consistency level is required. For example, for pizza delivery service, maybe the eventual consistency will be good enough. If your order is lost somewhere, you will place another order, or you will call to the Domino Pizza or some another and ask them where is my order, and they in manual way will replace your order. So if you would like to read more about consistency guarantees, it is best link, best website for this. It is this picture is also taken from this web page. Okay, let's move to another problem and related to the network. So in Hazelcast, we have, as I mentioned before, we have our own network implementation and network primitives. And this network is based on a so-called outbound queue and inbound queue. What exactly outbound queue is? It is actually the concurrent simple Java linked concurrent queue. Yeah, that it is used here. For what reason this queue has been added to the Hazelcast? When you would like to send some data from one member to another member, and call some send operation. This operation is not directly sent immediately those data via the network. Actually, it put this data into outbound queue, so in a concurrent linking queue. After this, there is some thread or several threads that reading from this queue and actually perform send operation, network operation, call some IO network API, and actually send data to another member. Why this implemented via queue? Because we would like to provide async way for communication and also provide way to resolve or solve the problem with slow network. If the network is slow, it will not block the process that executed in async way on the sender, because it should only put the packet or information that it would like to send to the outbound to the queue, and then continue execution or process another task in the same thread. And what this is, what types of messages put it in this queue? It's called packets, and packets is an abstract serialized form for operation that we would like to execute it on a remote member, or it could be data that should be replicated, or it could be a combination of operation and data. So based on this network primitives, we implemented the RPC remote procedure call protocol, like serialize some function that should be executed on another member. This function is serialized, put it into this outbound queue as a message. Also, then it will be transferred over the network. On another side, on another member, it will be deserialized. And here on another member, there are several also threads that reading from this inbound queue, and check type of this packet, and then deserialize it and execute, and depending from the type of the packet, execute or process the data that income to this member or not. On another member side, there's also so-called inbound queue. If, for example, packets arrive faster than threads can process this data, it will be also temporarily saved in this inbound queue. It is very nice and very smart approach for implementing communication in this way. Actually, the operation system also use the same pattern, but on a low level. So when you are trying to transfer some data over the wire, the operation system also use some internal buffers on the operation system level and put the data in these buffers before the data will be actually sent over the network. So this is a well-known pattern. But the problem with this pattern is that it can have several problems. It is the general problems, but in our network implementation, we also face it with those problems. There is a famous tweet that described those problems. The first one is exactly once delivery, and the second one is guaranteed order of messages. What is not what is the problem with this tweet? There's a problem that exactly once delivery appeared twice in this tweet and has number 2, while the guaranteed order of messages is after number 2, and so you can see how the problematic of network can be represented in this tweet message. And yeah, let's talk about the reordering problem related with our network implementation. It is related with how Hazelcast discover other members. So the Hazelcast cluster implemented in a such way that if you would like to add a new member to the cluster, you in the simple case, in a default case, you shouldn't even make any configuration for existing members or for this new member. You simply should launch this member in the same network. If you are doing this, the new member trying to discover and to join to existing Hazelcast member. How it is implemented? It is implemented in a way that when this new member started, it starts sending so-called join request. It is I'm trying to find it is a multicast request that sent to the whole particular network. And how it is implemented? It is implemented that we are trying in a while busy loop, sending this request with to all IP addresses in a cluster, not in a cluster, in our network, until some member, so-called the master member, will respond to this join request. If we have the response, so get master address is not null, we are return from this busy loop. Otherwise, we are sleeping a little bit. That's why it's called the busy loop or busy wait loop. It is the anti-pattern, but yeah, it was the architectural decision. So it sleep a little bit and then trying to resend this join request message. So in a timeline, this can be represented, this approach can be represented as in the following way. So we have two Hazelcast 1 and Hazelcast two members. Yes, Hazelcast 1, Hazelcast 2. And the new member, Hazelcast 3, that would like to join the cluster. And it starts sending the join request to all this member and doing this continuously. So if member is joined, so it's stop sending this join request and continue to operate in a stable way, in a stable way. It is in a best case. But what can happen if during this join request round, when the Hazelcast 3 member is trying to join to the cluster, it will be restarted. It means that some of those messages are already somewhere in a, can be somewhere in a inbound queue of other members. For example, in an inbound queue of Hazelcast 1 or Hazelcast 2 members. And if we restart the Hazelcast 3 member in this time, it will be restarted. It will have perhaps the same IP address, but will have the new unique ID address. After this Hazelcast 3 member has been restarted, it starts sending new join request messages with the new unique address. And if it is lucky, it could join the cluster very, very fast. But what will happen? It could happen that the old join request messages that have been stuck somewhere in a inbound or in outbound queue, or maybe somewhere stuck on the network, can arrive later than the join request from the restarted member. This means that the Hazelcast cluster member can consider this outdated join request message as a new message and will decide that this IP address will be used for the outdated member, because the Hazelcast member doesn't know that is it the new member, is it, or it is the former member, or it is outdated member. It based the decision only on messages with unique ID and IP addresses. So when this member receives the outdated message from the member that already not exist, it remove the actual active member with new ID from the cluster and waiting for the messages from the old member. So the cluster is partitioned on several members, and it looks like that suddenly the cluster partitioned on this member and on separate Hazelcast 3 member, and this Hazelcast 3 member couldn't join back to those two members, because those two members waiting for the Hazelcast member with those ID. But actually, the member with those ID will now join to the cluster, and the cluster not operate. It is a failure case, and to fix it, you should restart the whole cluster. How it can be fixed? To fix this, we should in some way detect and ignore outdated messages. But how you could do this if you have some messages that arrive to this queue and you don't know what message is new and what message is old, how you can distinguish those messages. And to do this, we can try to several things. For example, we can try use timestamps, but timestamps, as I mentioned before, is not a good way to do this because the clock on different machines could run with different speed and they may be not synchronized. So it is not a guaranteed way. As a solution that most of existing distributed algorithm uses is use so-called logical clock, and logical clock is based on so-called version number or something like this. And if you are sending new request or this request is sending from the new member, you should increment the version of this request. That's why another member or another cluster node could distinguish old message from the new message, even they arrived in a reordered way. Also, you could, and we have used this in our situation to fix this issue, you can try to save the list all previously disjoint members. So if something, if some member leaves the cluster, you are not completely forgot about this member, but you save the unique ID of this member somewhere in a list. This approach is also named as tombstones, and it is used in different databases to actually, when you remove some data from the table, actually it is not removed. It is there is a put its so-called tombstones that mark it that this data is removed and shouldn't be returned during the read operation, but it can be stay in a cluster for a long time. It is so that approach we incorporated to not allow to old member to interrupt or to broke our cluster. So, the next problematic moment that we have faced it is out of memory exception, and it is most complex and tricky one. Yeah, and it is also reported in our test environment, but it has not been fixed until this year. So you can see so that for 3 years it hasn't been fixed because it was complicated to fix it. So what was the problem about? The problem about, and it was related with our implementation of our outbound queue. As I mentioned that the packets in this outbound queue consume around 2 gigs. It is not a so big amount, but it was a test environment with limited memory. And if you run the same test in a production, there will be also the out of memory exception, but it will take more time to that this exception has been triggered. So the problem not depend from the memory amount. So what the source and the root cause of this issue. The issue is with our outbound queue implementation. As I mentioned before, for outbound queue, we are using unlimited concurrent linked queue. And if you have the slow connection, and from this side, from this side, and the fast client in another side that trying to send data, put it data into the cluster faster than those data can be replicated or pushed to another members, those data will be stuck in this outbound queue. And in some point of time, you will have the out of memory exception. If you are running, why we faced this problem only now and decided to fix this problem only now? Because initially Hazelcast has been used and deployed in a single data center, in a single availability zone. So the connection between members are fast enough, or very fast. But for in the last several years, the customers would like to put our members, to Hazelcast members, in different availability zones. So it is one availability zone, it is another one, it is third one availability zone, where the communication, where the latency is can be 100 milliseconds or even larger. So if data from the clients arrive faster than the latency plus the size of data that we should push over the network, we can have the situation when packets are stuck in this outbound queue, and the Hazelcast member is will be down with out of memory exception. What we should do with this situation? First of all, it was our issue, maybe not our issue, but initial design or architecture issue of the Hazelcast network primitives. The problem is that the outbound queue, this queue is unlimited. Unlimited in terms of number of entities in this queue, messages in this queue, and in terms of how much memory this queue can use, can consume. So what we should do, we should use some defensive mechanism. Perhaps in some way we could reduce message or packet size. One of the client decided to solve such kind of issue by zipping messages and packets. It replicate JSON data, so it is very nice zipped, and the size is reduced in several times. Also, we definitely should limit retries, because additional problems to and additional reason of the out of memory is that if the network is slow and the sender not receive the acknowledgement from the receiver in a defined time frame, the sender is trying to retry the sending of the messages. So in this queue, a lot of messages is a duplicate of the same message, because after some amount of time, when the sender not receive the acknowledgement from another member, it try to resend this message again, because it assumes that perhaps this message may be lost somewhere in the network. As I mentioned before, it's impossible to distinguish network failure from the another member failure, and impossible to distinguish from the slow member and from the slow network. The only way you can do is use something like smart exponential back-off retry, or retries with smart latency detector, something like this, to figure out if the latency between those members are huge, that the predefined latency. You should also increase the time between retries, between the retrying to send the message again. Yeah, so you should limit the number of retries and implement smart retries with adaptive time interval between those retries. Or perhaps the best way is to limit the buffer or queue size and apply some drop policy for old or maybe new messages if this queue is completely full. Because if we have the retry mechanism, it is not the problem if some messages will be lost or will be dropped by some drop messages policy. And another way is to implement the so-called flow control or back pressure behavior, and not trying to retry or send new messages until we receive some response from the receiver. In our situation, it was partial. This issue with out of memory has been partially fixed by implementing the flow control, but I will describe the actual problems a little bit later. So for now, we are moving to the Raft protocol and to the Raft protocol pain points. What pain points we will discover? We will discover so-called disruptive followers. We'll talk about leader flip-flopping. We'll talk about slow followers and problems with Raft protocol snapshotting. But we will start from the basics of the Raft protocol. We will not go deep into the Raft protocol. We only discover, or I will describe only some basics that are required to understand the next part of the talk. So the Raft protocol is based on a leader, and only leader can write messages or can respond to the read request. And clients only communicates with the leader to put message into the cluster and replicate it in a cluster, or read some message from the cluster. And if you are communicating with the leader always provides you so-called strong consistent guarantees. The leader is elected automatically, and if some member failed, some leader failed, then it will be detected by another members, and the leader will be automatically re-elected. And when the leader is re-elected, it is guaranteed by the Raft protocol that all information, all data that have been present on an old leader will be present on a new leader, so no information or data will be lost by this leader election protocol, and also based on a replication protocol. So the Raft protocol is leader-based protocol, and the first phase is leader election. After we have the leader is replicating data to members. How the data are replicated? Actually, it is. Let me erase. So if we assume that this member is the leader, and it receives some request to put some data into the cluster, the leader saves this data on its own member or memory or disk, and then replicate this data to another two cluster Raft cluster members. And this replication is done in a synchronous way. So the leader will not respond to the client until it receives the responses or acknowledgement from the majority of cluster members. In our case, we have 3 members, so the majority is 2 members. The one member of majority is the leader itself, and so we should wait on the response only from one other member. Another member is called followers. So to respond to the client, we should wait the response from one of the follower from 3 members cluster. Which of the follower responded faster? That's after its response, the leader will send the response to the client. So this means that the Raft protocol performance will be equal to performance of two fastest member in a cluster. To the slowest, if this member is slower, it means that the data also will be replicated to this member, but a little bit later in a background, and the client will not wait for replicated acknowledgement from the slowest member. So this is Raft protocol basics. And in theory, the Raft protocol will make progress as long as we have the majority of servers. So if one member dies in a 3-member cluster, it will be also fine, and the cluster can continue to operate with those 2 members. If these members after it was unavailable will join back cluster a little bit later, the leader will synchronize all messages that this member lost during it was unavailable or absent. Also, Raft protocol tolerate if messages will be lost during replication or will be delayed during replication. How it is implemented? It is implemented in a way that when a leader is trying to replicate a message and not receive an acknowledgement from some time frame, it retry to resend this message. With Raft protocol, we have no problem or issues with messages reordering, because each message has its number ordered number. And we also have no problems with messages duplication, because based on this unique ordered number, we can distinguish, is it replica, is it a duplicated message, or is it the new message. So the Raft protocol in theory tolerate if message delayed or lost, but it is in theory. In practice, it is a little bit another behavior. So let's talk about the leader election and what problems we can have with leader election. With leader election, not with the leader election, yeah, with the leader. When we have the leader to talk with another members to followers, as I mentioned before, and talk with them and signalize them that the leader is alive. The leader should periodically send so-called heartbeats. The heartbeats is implemented as append entries, but doesn't matter for the current moment. So leader, to signalize that he is alive, should periodically ping or send heartbeats to the followers. If followers not receive heartbeats from the leader for some period of time, they will start a new leader election. So to one of those member. So if the leader not sending heartbeat messages to the followers, these followers will start a new leader election round, and one of these followers will be elected as a new leader. And everything works perfect until we have an asymmetric communication in the network, or if, for example, not all members can communicate with all other members. So in this situation, the leader can communicate with this follower, but it couldn't communicate with this follower. But these two followers can communicate with each other. In general, it is not a problem to continue to operate for Raft protocol in this situation, because it has the leader has a majority. So the majority, so it can communicate with this follower and replicate messages to this follower. So it is not the problem for the leader to have such network behavior, but it is the problem for this follower. What problem is with this follower? As soon this follower not receive messages from heartbeats from the leader, for some period of time, it decides that the leader is dead or going down. So what the follower should do in terms of Raft protocol, this follower should start a new leader election. To do this, it nominates itself as a candidate, increase the term number. The term number means the term, the leader term number. Yeah. So if you have, for example, president, we can have first president, second, third, and so on president. The same is with the leader. When the new candidate would like to become a leader or president, it increases the term number. By this term number, we can distinguish all leader and the new leader. So the old leader has the term number equal 1. The new leader, if it will be elected, will have the term number equal 2. It is very important because we will see how it will impact to our leader election round. So when this member become a candidate and increase its term number, it sends the vote request to this folder. The folder parse this vote request, and from it only check this term number. And if this term number is larger than the term number of the existing leader, it decides that something happened with the existing leader because we have the new candidate, and it gives his vote to a new candidate and accept his vote request. After this, it also increase his term number, and this former folder becomes a leader with the term number 2. During this time, after this folder upgraded its term, and the old leader trying to send to this leader a heartbeat request, this folder responds to the leader that your term number in your heartbeat is outdated because I already seen a leader with a bigger term number, so you shouldn't be a leader anymore and should be converted to the folder. That's why this old leader change its status and converted itself to the folder, and this the former folder become a leader and continue to operate in a system, in a cluster, as a leader. Okay, that's fine, and the client should communicate in this case to the new leader. But what will happen after some period of time? Yeah, this leader also should send heartbeats to all followers. But due to the network problems, this leader is not able to send the heartbeats to this folder. And after some period of time, this folder nominate itself as a candidate, increase the term number, and wins the leader election, and again becomes a leader, and this member becomes a follower. So how it looks like from the outside? From outside, it looks like that leaders changes periodically. And during the leader election round, it is impossible to make a progress in a Raft protocol terms, in a cluster terms. So client couldn't figure out who is the leader at the current time, and periodically stuck with timeouts because they're waiting for a new leader, and the leader is flip-flopping between those two members. So we faced this situation when one of Hazelcast customer deployed the cluster across different data centers, and so it was one DC, it was second DC, and it was third DC. And between DC1 and DC2, there was some network configuration problems or firewall problems or misconfiguration or something like this. So members from DC1 and DC2 couldn't communicate with each other, and after this, the clients had very poor throughput, because most of the time leaders are flip-flopping between each other. How it can be solved? It is solved by introducing by pre-voting round. It is in terms of Raft protocol. I will go deep to this topic. And then second fix was so-called leader stickiness. Leader stickiness is implemented in such way that before, when this candidate ask for the vote for from this folder not immediately respond with yes, I accept you as a new leader, based only on term number. In addition, with leader stickiness protocol, we are checking is the actual leader is alive. So if this folder recently received the heartbeat from this leader and arrive and the new request from vote request arrived from the candidate, this request will be rejected because folder already has an active and healthy leader. So this addition to the election algorithm, election protocol, is called the leader stickiness. And by adding this small check, we have solved this issue. Let's move to the log replication. With log replication, as I mentioned before, a leader is responsible to consume messages from the client and then replicate those messages to followers. When this message is not definitely so, before the leader receives an acknowledgement from majority or from one of the followers that its message is successfully replicated. On a leader, this message is in a so-called uncommitted state, because we don't know are those followers receive those message or not yet. And only when we receive acknowledgement from the majority of members, in a case of 3 cluster members, it should be only one member, this message will be committed and responded to the client that this message is successfully replicated to the cluster. Now, to replicate the message, we are using the leader use so-called append enter request. And inside this request, he also pass the message body. And when the follower receive the message, it responds to the leader with append acknowledgement. And when we have the majority, the leader is put this new message into committed state and respond to the leader. If we have no responses from the majority of members, the client will should continue wait for the response. So in this case, if we have the slow network, the client throughput will be not very good, but it is only related with throughput. So the leader will never send the response to the client if it will have not the majority of responses from all members. This way that the Raft protocol guarantees that consistency of replication and that messages will not lost. Okay, that is the best case scenario. But what will happen if some of the member has a delay? So what will happen if this link to some follower has a latency bigger than another, a network link latency, or if or what will happen if those members deployed in different data centers or in different availability zones. And in this case, we can have a problem that I called like latency amplification problem. So we can have, it is not related to the Raft protocol, it is related with general distributed system and database theory. There could be write amplification problem when you are write a bit of information, but this information duplicated or amplified in several times during the replication. We can have retry amplification, especially if you have microservices. Yeah, and you retry some operation on top level of microservices. It brings to operation will be retry on all microservices, even only one is a bad state. And now we can have the latency amplification problem. What this problem is about? As I mentioned, let's assume that this leader is deployed in one availability zone, and those two members, followers, deployed in another availability zones. So the latency between those followers may be 1 millisecond, and the latency between followers and leader could be, for example, 100 milliseconds. How cluster will behave in such way? In such way, yeah, in such situation, actually the performance, the throughput will be not good because the leader should communicate with one of the follower. So the latency for client will be 100 millisecond plus minimum, even not 100 millisecond, even larger. Why? Because when the client connect to the leader send replicate data to the follower, and we have 100 millisecond that this message pass to this follower. But to respond to the client, leader should wait for the response from the follower. So the leader is waiting while the follower sends the acknowledgement, and this is additional 100 milliseconds. So in total, in such deployment scenario, we have 200 milliseconds delay. Yeah, for each message to communicate to that should be put it into the cluster. The situation may be even worse. Why? Because actually in our old Hazelcast client implementation, the client was not aware who is actually the leader of the among those members. So in a client, they have been implemented the round-robin algorithm, and client randomly select which next member it will be connect to replicate the message. If it is the leader, it's fine, but it could be this folder or it can be this folder. In this case, the number of network hops will be increased in 2 times. So the first network hop is communicate with the folder. The folder in this way will be work like a proxy and resend this request from the client to the actual leader. So it is one additional hop. The leader will send back this message to this folder to execute the Raft replication protocol. After this, the folder should respond to the leader with acknowledgement message. When the leader receives the acknowledgement message, it should respond back to this folder, and the folder should respond to this client. So if we try to count the number of network hops in such situation, it will be client to follower 1 hop, follower to leader 2 hops, because follow to leader 1 hop, and then leader should execute the Raft protocol send message and receive the acknowledgement, so it is 2 hops, and the leader should respond to the follower that works like a proxy, and the follower should respond to the client. So in total we have 6 hops, and if this network hops is 100 milliseconds, it will be 600 milliseconds additional delay. So we have faced this situation. We have one of Hazelcast clients also deployed their cluster in different availability zones, and after this he realized that the throughput is extremely low. And after this, we decide, what is the throughput difference? It is the throughput if we have no delays between cluster members. And this is the throughput if we have, for example, 1 millisecond delay. It is 2. The scale is so the scale for throughput without latency is so huge that the difference between throughput with some latency is looks like very close. So the difference in throughput without delay and with delay in such case is more than 10 times. So we decided to implement a smarter way to operate in such situation, and we have added the direct to leader routing. And if in such case, if even the network has the latency problem, but communicating directly with the leader will eliminate this additional network hops. Yeah, and they will be only this network. They will only those network hops. Yeah. Yeah, it was implemented like direct to leader routing, and another solution was let's not allow to be the slowest member in a cluster a leader. So if we put a leader in the data center where it has the majority of members, the performance of the cluster will not depend from this slow member, but it will be depend only for majority, and those majority are in the same data center. So we also implemented the scenario where we can mark or labeled our members and tell some of members that they couldn't be a leader. It was a solution of such problem. But after this, when we solved this problem in this way, we have faced it with another problem, and this is problem about what is the better, one slow faller or two slow faller. If we take a look at this picture, the answer is obvious. If we have one slow faller, for example, with 100 millisecond latency, it is better because the cluster performance only depends from those member, and the latency to this member, one slow member, will is not taken into account. If we have two slow fallers, for example, if the link connection with this member is also has 100 millisecond latency, it means that the cluster performance and throughput will be poor and will be look like this. So with one slow faller, we should have such throughput. With two slow fallers, we will have the fallen throughput. So it seems that the answer is obvious. But when we start testing this deployment scenario, assuming that we have 10 millisecond latency to this faller, we figure out to the following, we have faced it with the following behavior. Let's try to understand what can happen with if we have some slow member and we have the intensive traffic from the client. So in traditional Raft replication protocol, the leader is trying to replicate messages, to this faller and to this faller. For this faller, the fastest for the fast faller, it received append acknowledgement and could respond to the client. While for the slow faller, we don't know what has happened with this append entry, but it doesn't matter. The cluster can progress with this member. It is everything fine if we have one message and that arrive from the client. there will be no problems. But what will happen if immediately after the first message with C equal 41, the client sent the next message with D 42. In this case, for the fast leader, for the fast follower, only this message with message D will be replicated. But for the slow follower, the leader marked itself that he already hasn't received the response from its previous message, 41 message. So when the message D arrived, this leader, to optimize network traffic, is trying to replicate the new message D and the previous message C, from which he hasn't received the response from this slow follower. And it is put it into the append request, two messages, 41 and 42. Okay, then a new messages will arrive from the client, and the fast follower will consume it one by one. But for the slow follower, the leader will try to replicate those messages in the following way. So as we have mentioned, as we saw before, the first request was with only one message. The second request with message D was with previous message. The next request from the message E was with all previous messages, and so on. So if the leader has no response from the follower regarding the state of previous replicated messages, it is trying to replicate those messages simultaneously with the new message. And after this, let's move back to our outbound queue design. In our outbound queue design, all these messages are put into the queue as packets. So this message is message C. This message is message D plus message C. This message is this packet is message E plus message D plus message C, and so on. So in this queue, we have the snowball of messages that where the part of these packets are duplicated. These packets are stored in outbound queue in a serialized form, so it is the binary representation, and it is impossible to figure out what the existing packets contains, and we shouldn't, for example, trim some messages from one packet because they are already present in another packet, because they are presented in a serialized way. So we have the situation that this packets, number is increased, and the size of the packet is also increased. And if you assume that there is the message is not the simple number, but it is, for example, 10 kilobyte JSON file, in nearest time, this server is put it into out of memory exception, falling down with out of memory exception. And that's why we saw in this outbound queue, in some case, 8 gigs of messages. So it was several thousand packets in this outbound queue, and each packet is a little bit larger than the previous packet. And the number of these packets are also huge. And and that's why the Hazelcast member is failed with out of memory exception. What we can do? There are several possible ways to solve this situation. We can do like Microsoft, in Microsoft, in CosmoDB, in the documentation, he said that if data centers or cluster are more than 5,000 miles from each other, we will block the replication, and we will not provide the strong consistency for such kind of deployment. So the solution is simple. If the latency between member is large enough, we are not supporting this case. In our situation, we are also would like to tell our customers that perhaps you shouldn't use such deployment scenario. But then customer said, okay, I will choose another product as in-memory replication system, and your company will lost several a big amount of money. And our management decide we shouldn't lost this customer, so you should do something to support the network with high latency. So we couldn't answer to this, we couldn't solve this problem like Microsoft did, and we should in some way to figure out how to fix this. The way to fix this is to implement the flow control, another solution, limited queue, as I mentioned before, and back pressure. Our solution is implement flow control. But when we implement the flow control, we slow down in general the whole cluster, and we slow down clients. So we put but the network problem to the side of the customer, because they couldn't send their messages in so intensive way. Have we solved the problems? Look like this. And why? Return to the question: what is better, one slow follower or two slow follower? With two slow follower, we have not such out of memory problem, because if we have two slow followers, the leader couldn't commit a new messages faster than those both slower member, slow followers. So the throughput of the system is equal to the slower followers, and that's why there is no big difference with in two followers like we saw before, because all followers consume and accept messages with equal speed, with the equal speed. There is no situation when one member consuming messages faster than another one, because the problem that we face it with out of memory was related that those members consume and replicate data faster than this member, and the data difference between the fastest member and the slowest member is put it into the outbound queue and trying to replicate it. If both members are slow enough, there is no difference between the replication between messages that replicated for both of them. So in this case, the two slow members was better than the one slow members. Why? Because with two slow members, there will be no out of memory exception, and with one slow member, there has been the out of memory exception. Okay, we have solved this issue, and after this, we run another bunch of performance tests. These tests are running with two slow followers. Yeah. With two slow followers, it is we manually increase the latency between leader, so it is the leader, and there are this is the leader, and there are two slow followers, and we increase the latency with leader and with slow followers, starting from 2 milliseconds and 4 and 10 milliseconds. The cluster was stable, no out of memory exception, no data loss, and the throughput going down, it is logically depending on latency. With 2 millisecond latency, the throughput was something like this, with 4 like this, and with 10 milliseconds was like this. Okay, after this, we decided to run the same tests, performance tests, but with one slow follower. So with one slow follower, with 2 millisecond latency, it was such throughput. What was our expectation with 4 millisecond latency and with 10 millisecond latency? The answer is we expected the same throughput like was with 2 millisecond throughput. Why? Why increasing latency with one member shouldn't decrease the throughput? As I mentioned before, that is the leader, that is slow follower, and this is fast follower. As I mentioned before, cluster Raft protocol can progress if the message is committed on a majority of members. So if it is a fast member and it is the slow member, the performance of this slow member shouldn't affect the performance of the cluster. And that's why we expect that when we have fixed the problem with out of memory exception, related with snowballing of messages, after this we have expected that the latency of the slow follower should not impact and will not impact the cluster throughput, and the throughput will be stable and not depend from the slow follower. But what happened during our test, and it was very surprising for us. With 4 millisecond latency, cluster start behaving in a very strange way. So we have some throughput spikes, but Then we have the several seconds, the period of time when the throughput was 0. So during this time, it means that the client not receiving the acknowledgement from the leader and waiting for response from the leader. It means that the leader in some way stuck why it is performing replication or or doing something like this. But yeah, it was strange. But we decided to test the performance when the increasing latency only with one follower to 10 milliseconds. And what we face it with? We face it with that in the system start, it was something happened, but after even 30 30 seconds, the throughput was equal 0, and in the log we have found out of memory error. We was very surprised because actually we have fixed the issue with outbound queue, but we have the same kind of the problem again. Again, we have the problem with out of memory exception. After digging into the codebase, into the log, we have found that we have the next problem related with the Raft protocol, and this problem is related with the Raft log snapshotting. So what is Raft log and what is snapshotting? In theory, and as I drawing here, there is a number of messages, and those messages that has been replicated saved in a so-called Raft log. Raft log is a limited sized array. It couldn't be unlimited, otherwise we have out of memory exception. So it is limited. But for example, if we have such messages like x assign 3, then x assign 2, and then x assign 0, and then x assign 5, there is no sense, no reason to save those messages, to save all those messages or comments, because the final state of the x is equal 5. So as you can see, if we apply all these comments, all these messages, this log, message log or Raft log, could be snapshotted only for two entries: y equals 7 and x equal 5. This process is called snapshotting, and Raft protocol is periodically running this snapshotting. And how it works? The old Raft log is snapshotted and created a new Raft log, only with snapshotted data from previous log. So in the following example, it was old log, and this is the new Raft log. Logically, yes, it is logical. But after this snapshotting is happened, the new version of the Raft log that is present on the leader should be replicated on to the folder. Yeah, to the folder. Yeah, and if the snapshot size of this log is not so large like this one, we have only two variables, so the snapshot is not very large. But if you have in a log several thousand of distinct variables, and each variable has some large payload, the snapshot size of this log, the snapshot of this log may be equal to the initial size of this log. So if in a log you have a lot of distinct variables in a log, after snapshotting, we have no operations that can be skipped or deleted from the log. So the snapshotted log will be almost the same as an initial log. After we have the new log, as I mentioned, this log is transferred from the leader to the follower. And if the size of this log is huge, several gigs, it means that the leader should push over the network the whole version of the snapshotted version of the previous log. And if we have the slow network connection, yeah, with this member, we are putting this snapshot into the outbound queue. Because we have the latency problem with this member, and we also have the timeouts and retry policy for this snapshot operation, we return to the previous issue. So while this snapshot is trying to push through the slow network, and the leader not receives the response from the follower from another side, it is trying to retry with this install snapshot, with this to retry to resend this snapshot. And if the snapshot is take 1 gigabyte, it's in the outbound queue we will have 4 gigabytes of the actual the same snapshot that is put it in by retry operation. What we can do is this: we can in this way we can try to apply snapshot deduplication, because there is in opposite to the append request snowball, when each packet were distinct from each other. In this case, the snapshot is equal each other. So this snapshot are equal to each other. So we can try to detect the same packets in an outbound queue and apply the duplication policy, not put this snapshot again in an outbound queue if the queue already has the same packages. And another way is the same limited queue. We have decided or apply some exponential Bykov network latency, but we decided to do the snapshot the duplication as the simplest way, because for other way, other fixes, we should change the code base a lot. So we decided to make local changes in a code base. After we apply the duplication, we have no out of memory error. It was good, but the behavior also was strange enough. So this is the throughput, and we have the periodical spikes of the throughput, and we have 40 seconds delay. between these spikes. And during this, what actually happened between these spikes? We assume that during this time, the cluster, the leader, is trying to push to the slow follower, Yeah, this is the slow follower. The slow follower. This snapshot. Yeah, but you may ask, okay, this leader is trying to push it to this folder, but why it is impacted to the throughput? Because the throughput, as I mentioned several times, depend only on from the fastest members, the leader and the fastest follower. Why we are pushing this 500 megabyte snapshot? Why we have throughput in this during this time is equal 0? And the answer is very simple. Only in a picture we have separate communication channel from to those folders, fast and slow folder. In reality, the server has physical server or virtual server will have has only one network interface. So all operation and all connection to fast and slow follower is operated. All data are passed over the same network interface. And if we are trying to pass such amount of data through this single interface, we have faced the problem that called is network or traffic congestion. What is it about? It is about the very simple example, the similar example. For now, cars' speed are much higher than 100 years ago, but the average traffic speed in London are slower than the 100 years ago. Why it's happened? Because when the network is trying to push a huge amount of data, it in some way blocks all other network communication and all other traffics with other member. So it's I am not definitely no, but we are assuming that it is the problem with on the level of the operation system, that the operation system is trying to push, in our case, 500 snapshot over the slow network connection, and this block as a traffic communication even with fast members. This experiment, this performance test has been performed on AWS EC2 instance with dedicated network interface. With good network interface. So the assumption is that perhaps it is also related with AWS network policy. Yeah, but because in my local experiment in Docker container in a local laptop, everything was fine, and only in EC2 instance we have such behavior. What we can do, we haven't done this yet, and I hope my team implement it and fix this in some way. But the idea was to split this package snapshot on smaller packets, on smaller chunks, that between those chunks another traffic could also pass over the network. Also, in other Raft protocol implementation, I read that there is a parallel snapshot replication, for example, from another folder. In this way, the leader shouldn't be busy to work with the slow member. And yeah, for now it's the solution that we will have in Python. And to summarize, yes, it was the last example of the problem, and the takeaways are the following. When you design something, especially related with data, when you demand from the or require some consistency level, data consistency level, try to understand what consistency guarantee you need. If you would like to have strong consistency guarantee, yeah, it means that the throughput may be not very good. If you find that some message can be lost, or the cluster may not consistent, you could put your system into eventual consistency guarantees, and but the throughput in this case maybe will be better than in the case with a strong consistency. Think about message order and delivery guarantees. If the network and different products in some way, they not always guarantee the order of messages. For example, Kafka only in one the topic, yeah, can guarantee the order of messages. If you are using several topics, yeah, the order between the messages in those two topics are unpredictable. Also, you are maybe familiar with exactly one delivery problems, or exactly one delivery guarantees, or at least one delivery guarantees. Different system provide or does not provide these guarantees. For example, Hazelcast for some data structure implemented exactly one delivery. For another data structure, we not implemented such guarantees, and you should read documentation for which data structures these guarantees are implemented, and how is it, if it is possible, how to change or tune these delivery guarantees. Also consider retries like a drug. Yeah, in some way, in a smaller amount, it can help like medicine. But if you use it in an uncontrolled way, their tries can kill. This is a very nice article at Amazon about timeouts, retries, and backoff. Also, that this lesson I have learned during the last year. Always test your system in a different deployment scenario with unequal latency between members. So when our cluster work deployed in a single data center, everything was fine. When our cluster members has been deployed with network with equal latency, it was also fine. But when we deployed, when our customer deployed the cluster members in data centers with different latency, for example, 10, and here is 100. This deployment scenarios cause the huge problems that the product itself has been not ready to tackle, and we should change some initial architecture design and re-implement the part of the system here to work in such conditions. Yeah, and it is the challenge. And also try to operate your system with asymmetric network latency, deployment in different availability zone, pausing and unpausing virtual machines. So implement that, name it as house testing, but in a controlled way and with significant load like production load. Because it is very inconvenient when you hear about your problems in your system, not from your testing department, but from your customers from production. I have spent several days on a customer call meeting, and it was terrible when we are trying on production to solve this issue and trying to figure out where is the problem, because we blame it everything. We blame it network, we blame it virtual machine, we blame it Docker, we blame it another subsystems that is running in those network. Yeah, and we have built a lot of conspiracy theory around this problem, but actually the problem was inside our product, and the problem was that we haven't even tried to test our system in such deployment scenario. And in general, it was not decided, it was not designed from day one to operate in such deployment conditions. So if you would like to, if you are planning to use your system in some such deployment scenario, you should definitely test it. And don't forget that there are a lot of pieces of puzzles, JVM, VM, host, network, another three letters that I don't know even how to translate, and they can fail in some point of time, and you cannot stop it, and only you can do, you should be ready for this, and you should welcome failure and be ready for those failure. And to be ready to this, for those failure, and how to implement high load or distributed systems, there is classical books that you may read. This design data intensive application from Martin Kleppmann, very nice but not so famous book about understanding distributed system. Database internal from Alex Petrov. He works from for on Cassandra database from Apple. And also, if you would like to have a crash course about distributed systems, there is a best video that I could advise you to watch. It is Martin Kleppmann, yeah, the author of Design Data Intensive. It is the set of lectures that he read for the Cambridge University, and after I think 8 lectures, you will be familiar in general about how to design, about the problems in a distributed system. So that's the end. Yeah, I have spent 2.5 hours. Sorry for this. My previous version of this talk was 1 hour, but for now,
Thank you, Andrii, for such a wonderful talk. It was great. Guys, if you have any question, don't hesitate to ask them in the comment section to YouTube video. I see 2 of them. Andrii, I will highlight first. The first one. What replication options did you explore and which worked the best?
The usual answer in computer and programming is it depends. It depends from what so-called consistency guarantees you would like to have. So as I mentioned before, there is the line, and this line has the beginning at the end. In this, at the beginning, assume it is a performance, and this is consistency. Yeah. If you would like to have the best performance, your system during replication will not be consistent. So you should use so-called AP data structure that guarantee you, that provide you availability. So the best effort, best effort for replication without waiting for acknowledgement, without any guarantees. But the performance will be the best. But in this case, you can lost your data. In the other end of this line, it is consistency, and the performance will be very bad, because in as I mentioned, in 3 members cluster, the client should synchronously wait for 2 members response. If your cluster size will be, for example, 5 members, the majority will be 3, and you should synchronously wait response from 3 members. In this way, in this algorithm, your system will be consistent, but the performance will depend from the performance and from the network latency between those members. Also, as I mentioned, there are maybe additional problems if you have some slow member, and as we have faced it in my experience, there can be the problem with out of memory exception, network congestion, and so on. So first of all, to answer the question, you should decide what performance you would like to have, and what consistency guarantees you would like to have. If you are if your system is fine to that some data may be lost, you can move to the AP. If you are not tolerating that any data loss, you should move to the consistency and use some consensus protocol. Or perhaps you may use something between, as I mentioned, between those consistency guarantees. There are intermediate. There are also intermediate. Sorry, I should select. There are intermediate consistency guarantees. Not all, not any distributed system implements them. Maybe the best database when I saw all of them I implemented, it is MongoDB. Yeah. In MongoDB, you can specify all of any of these consistency guarantees, and this is consistency, and this is performance. So, but to understand which level of consistency is fine for you, you should understand what guarantees each of this level provides you. As as analogy in databases, when you asked what transaction isolation level you should have, the best level and the most strict is serializable, but you are not applying it by default because maybe for your case read committed will be also fine. So the same with distributed system with replication, you should clearly understand what business is required for you, what the guarantees in your case is more suitable.
Thank you, Andrii, for such great answer. And we have the next question. Probably it would be a more personal one. And I guess we could switch to Ukrainian language because, Ukrainian have different context about UKU, university and stuff so on. Андрій, є два варіанти. Задизайнити все з нуля або кинути все і піти викладати в УКУ.
Ну так. Ну, я вже викладаю в УКУ, але ще все не кинув. Ну, задизайнити з нуля це в наступному стартапі, до якого, можливо, доєднаюся, може й ні. Також радий вітати тут багато знайомих, якщо вони ще тут присутні. Денис Смаковський, ми пишаємось тобою. Ось Денис Смаковський є колишнім викладачем КПІ, зараз він служить, захищає нас. Оля, також привіт, якщо ти ще тут гупало, вона з Oracle. Так що приємно, що ви принаймні завітали на початок.
Думаю, всі дослухали до кінця. Добре, ми тоді будемо рухатися до завершення. Я пошарю свої слайди закриття. Це буквально буде декілька хвилинок. Так, друзі, хочемо вам подякувати, що ви доєдналися до нас. Дякуємо нашим партнерам і не забувайте підписуватися до наших соціальних мереж: Twitter, Facebook, Telegram, все по стандарту. Бажаємо вам удачі і stay safe. See you.
До побачення. Слава Україні!